is the top of the hour. So we've got a good number of people, but a few more people are going to filter in. And so let's go ahead and get started. And so hello, everyone, and welcome to the December NASA Night Sky Network member webinar. We're hosting tonight's webinar, as usual, from the Astronomical Society of the Pacific in San Francisco, California, and our remote site in Potsdam, New York, for those of you who are familiar with that part of the country. We're very excited to present this webinar with our guest speaker, Dr. Jerry Bonnell from the University of Maryland and NASA's Astronomy Picture of the Day. Welcome to everyone joining us on the live stream. We're very happy to have you with us. These webinars are monthly events for members of the Night Sky Network. For more information about the NASA Night Sky Network and the Astronomical Society of the Pacific, we'll put some links into the chat in just a couple of moments here. So before we introduce Jerry, here's Dave with just a couple of announcements.
Hi, folks. I'll get this done real quick for you. First of all, just so you know, if you got the alert a little late for this webinar, some messages got stuck when I sent this out and I managed to get them out. So apologies if you got a late notice, but you're here now and that's great. And just a heads up also for folks who ordered pins the past few days, getting them stuff wrapped up. They will be shipped either later this week or early next. We had a bumper crop of orders, which is lovely, but they will get to you soon. And I'll send you all notices individually after this. Also, one more thing, it's just the last chance for me to say this. It's a great time to add your club's upcoming events to the NSN calendar for 2022. As long as your holiday season isn't too hectic, of course. When that happens, by next year, you already have all your events added in advance. It's making updating and reporting on them easier. And plus, you may qualify your club to win one of 20 Galactic Quest 4-H kits. And I'll put those links in the chat in a second. And that's it as far as I know. I won't be holding off our main topic any longer. Back to you, Brian.
All right, thanks, Dave. So for those of you on Zoom, you can find the chat window and the Q&A window at the bottom edge of your Zoom window on your desktop. Please feel free to greet each other in the chat window or to let us know if you're having any technical difficulties. You can also send us an email at nightskyinfo@astrosociety.org. If you have a question for Jerry tonight, please type it into the Q&A window. That really helps us keep track of your questions and we don't lose them in the chat. And speaking of the chat, another reminder, please make sure that you select everyone at the bottom of the chat window so that we can all see your greetings. We'd love to hear from all of you out there. Okay, so I'm going to hit the record. So again, welcome to the December webinar of the NASA Night Sky Network. This month, we welcome Dr. Jerry Bonnell to our webinar. Dr. Jerry Bonnell received a PhD in astronomy from the University of Maryland at some point during the last century. He has since enjoyed working on a variety of astrophysical satellite projects at NASA's Goddard Space Flight Center, including the Cosmic Background Explorer, the International Ultraviolet Explorer, the Compton Gamma Ray Observatory, and the Fermi Gamma Ray Space Telescope. Sounds like a regular tour of the great telescopes there, Jerry. While his research interests have wandered across the entire electromagnetic spectrum, they have most recently focused on the time histories and spectral evolution of cosmic gamma ray bursts. He's the author of some popular books, reviews, and magazine articles on astronomy and high-energy astrophysics. And he's also the founding editor and author of Astronomy Picture of the Day, along with Robert Nemiroff, who we had last year for this particular program. They began that together in 1995. Dr. Bonnell lives with his wife, an art historian in Greenbelt, Maryland, USA. So please welcome Jerry Bonnell.
Thanks, Dave. Thanks, Brian. At some point, I share my screen, right? This is how good I am.
Whenever you're ready.
We might be sharing a screen now.
It looks exactly like we want it to look.
Okay, thanks, Brian, and thanks, Dave. Thanks for inviting me to give the Night Sky Network webinar for December 7th. I understand that my colleague in arms, Robert Nemiroff, often gives such webinars to the Night Sky Network. So this is my first time. Bob Nemiroff and I have been doing Astronomy Picture of the Day, a website run out of Goddard Space Flight Center for a few years now. I think it, as mentioned, in 1995 is when it started. And tonight, I'd like to show you some pictures from that website that we featured in 2021. So, and I sort of like the travel log metaphor. So I think I'm going to try to do something like postcards from the universe. Pictures from Astronomy Picture of the Day, 2021. The one on the title slide here is as it says, Apollo 14 heads for home. I wonder if it looks familiar to you. There's actually a very famous image from Apollo 8, the Apollo 8 mission of Earthrise, the Earthrise over the limb of the moon. This is a similar one from Apollo 14. So what you're seeing here is, well, Apollo 14 actually would have been in 1971. So that would be 50 years ago. This 2021 would be its 50th anniversary. Apollo 14, I think, was Shepard, Rusa, and sorry, if I can check my notes here. Oh, Mitchell was the lunar module pilot. So this is, but this is all three of them in the command module coming around the far side of the moon. And as they orbit around the moon, they see the crescent Earth rising there on the limb. So that's the far side of the moon, the unfamiliar side in the foreground there. They see it rising because of their orbital motion, right? When Shepard and Mitchell were actually on the lunar surface, the Earth just hangs in their sky. It's more or less steady at a spot in their sky. But because of the orbital motion, the moon is locked in tidal rotation, and because of the orbital motion, they can see the Earth rise. Anyway, Apollo 14 heads for home. It's a good start to the travel log here. So let's travel to France for a moment. This was, I thought, an interesting submission late in 2021, but it's actually a photograph of the summer sky, a sort of late night summer sky, from a plateau in the French Alps. So this is at substantial altitudes, say maybe 7,000 feet or so. The sky's very clear. The night sky is very clear here. The foreground is lit by moonlight. So this is a picture taken near moonset. And these two friends have been hiking through the Alps for the day, and they're admiring the view. It's an interesting view, and it strikes me that it has it has a literally extragalactic perspective. So I'd like you to look with me for just a minute. It's also very much, it also reminds me, it's very evocative of what you would see with the eye if you were there on this hike. This is the Milky Way. You can sort of see running down the left side of this view here, of this frame here. So this is Cassiopeia. This is Perseus down here. So this is the stars in the plane of our galaxy, the Milky Way. Right above them here, I see another galaxy, the Andromeda galaxy. Also, if you're a fan of the night sky, I bet you've seen the Andromeda galaxy. That's it's an easy naked eye object, an easy extragalactic naked eye object. 2.5 million light years away is how far you're looking there. I think the photographer Martin Lafranc realized maybe only after he made this image that right down here, right between the two friends, is another galaxy, the Triangulum galaxy. M13 is this very fuzzy spot here. So these basically are the three galaxies in the local group, the three largest galaxies in our local group. M13 is the smallest, Andromeda is the largest, Milky Way is the middleman in size there. Quite an interesting extragalactic perspective, I think. Had the two friends, let's see if we can do this. Had the two friends actually been on that hike 5 billion years from now, they would have seen something like this. The very top frame here is an illustration, not a photograph of a horizon, and this is the Milky Way galaxy, and this is what the Andromeda galaxy would look like about 5 billion years from now, when Andromeda and the Milky Way galaxy begin to merge. Andromeda is headed for us, although it will take a while to get here. The sky will look really spectacular when it does get here. In fact, the third galaxy in the photograph, the galaxy between the two friends, was the Triangulum galaxy. That's this frame here. A telescopic image of Bernard Miller. I really don't have a good image to illustrate this, but ultimately, of course, the Triangulum galaxy will join the Milky Way and Andromeda in a merger. I just note the Milky Way plus the Andromeda galaxy, you would probably call that galaxy Milkdromeda, for what it's worth. And I tried to think of something to call the three galaxies when they were all merged 5+ billion years from now. So I went for Trimilkdromeda. I don't know. I expect there are people that could do a better job. Have a few images of Mars here, sort of snapshots from the Perseverance mission. Mars 2020 mission actually landed on Mars in February, I think, of 2021. This top one, Perseverance, How to Land on Mars, is actually a snapshot of the Perseverance itself being lowered to Mars surface on these three cables from the descent stage. The descent stage is rocket powered. So it's a rocket powered sky crane, if you can imagine, was lowering this rover down these cables to the Martian surface. These cables, I have in my notes here, these cables are about 7 meters long. And at this point, which is actually a frame from a video that's being made with a camera on the descent stage, the rover itself is about 2 meters above the surface at this point. You can see the rocket engine exhaust is blowing the dust around the surface of Mars. And Jezero crater was a delta near one side of Jezero crater was the landing site. This is an electronic umbilical signal cable. In fact, it's connected it's connecting to the computer on board the Perseverance rover. And it's almost a selfie in the sense that this image is being recorded by the computer, being transmitted through this cable to the computer on the rover for a later broadcast to Earth. Of course, after the sky crane drops off the rover on the surface of Mars, these cables are detached and the descent stage flies away nearby and crashes far enough away so as not to contaminate the landing area. Just to prove, well, I'm sure everybody's seen images from the Perseverance Mars rover mission. This is say a month later or so. This is a selfie, Perseverance rover, and this is Ingenuity, the helicopter, the little Mars helicopter it brought with it. So a few snapshots from Mars. This top one, we're still hanging out on Mars here, except this is the Curiosity rover. It's a mission that's been operating on the Martian surface since 2011, and I just thought this was an interesting shot of clouds on Mars, night shining clouds on Mars. This butte in front here, this sort of layered mound, is called Mount Mercou. The Curiosity was parked nearby. In this image was made near twilight. And so the sun has set, but on Mars, as seen by the Curiosity rover, but the clouds are shining still because they're very high altitude, extreme altitude clouds, and still in sunlight, even though the ground is in shadow. So on Mars, those clouds would probably be carbon dioxide ice, dry ice, crystals, very small, as I say, at really extreme altitudes. We have that same sort of thing going on Earth. The bottom panel shows you Northern Summer Twilight by Justin Anderson. It showed the clouds that you see, these silvery, wavy clouds along the horizon in the distance there, are not dilucent clouds, night shining clouds on Earth. They're water ice, though, I think, and we tend to see them on Earth in the summer months at very high latitudes. Once again, the sun is below the horizon. And you see these clouds shining because they're still in sunlight at such extreme altitudes. I guess one big difference might be that in Justin Anderson's view, all these little green spots of light are fireflies. Probably not fireflies on Mars. When I was putting this together, I think I had trouble getting away from Mars. But let's do a few more Mars pictures. Actually, the one at the upper right is not so much Mars, but it does look like it. On Mars, the sky is this reddish brown because in the Martian atmosphere, the Martian atmosphere is dusty. There's very fine dust on Mars. The dust is iron oxide. That's rust. That's why the dust it colors the sky sort of a reddish brown. The Martian sky sort of reddish brown. And on Earth, of course, the sky is blue, but in this, the upper picture here was taken in the Swiss Alps at a ski resort on planet Earth, and the dust that's in the atmosphere that's scattering the blue light and turning the atmosphere of Earth. This reddish brown is from the Sahara. It's the Sahara dust storm blowing across the Swiss Alps there. Looks like Mars. Another image that caught my eye was also a little like Mars by Robert Barsa here. This is it's a little planet projection, it's called. It's a 360-degree panorama with the nadir at the center. So it's been projected, and this is the horizon, and this is the sky. It's an all-sky panorama. Robert Barsa's at San Pedro in Chile, in the Atacama Desert. And the Atacama Desert is what the foreground here is. It looks a lot like Mars. You have to, it's a southern hemisphere sky, so I bet you do recognize some things in the sky, but for example, this is Orion. Although from the southern hemisphere perspective, you might notice it's upside down. So there's a Betelgeuse down here, Rigel up here. The large Magellanic Cloud, small Magellanic Cloud, good southern hemisphere objects. And actually in Barsa's photograph, he did get Mars as well. This is Mars in the night, in the southern night. Oh, we're still cruising through the solar system here. I guess in 2015, maybe Rosetta mission was launched in 2014. Arrived at Comet Churyumov-Gerasimenko, and this is a photograph from the Rosetta spacecraft, the European Space Agency's Rosetta mission spacecraft. It's actually a photograph from the lander, the Philae lander on the spacecraft, which is still attached to the spacecraft in this picture. This is the sort of the sun glinting off the solar panel, one of the spacecraft's solar panels. And at the very top, you see this sort of double lobe nucleus of Churyumov-Gerasimenko. If you get tired of saying Churyumov-Gerasimenko and you don't want to call it Rosetta's comet, you can always call it Comet 67P. It's a P for periodic. It's the 67th on the list of periodic comets. And it has an orbital period of 6 point something years, 6.4 years, something like that. And so this Rosetta mission arrived, as I say, I think in 2014 or 2015, stayed with the comet, explored the comet. The Philae lander actually landed on the comet, and the Rosetta spacecraft was actually driven down to the comet during its last perihelion passage. But it's come back. Its new perihelion passage, I think, was in its most recent perihelion was in November, early November. And so the comet was back in our skies. This is a nice picture from Rolando Lacustri of Rosetta's comet 67P while it was in the constellation Gemini. These are stars in Gemini, and I think this is light coming in from Pollux there, Beta Geminorum, one of the two bright Gemini twin stars. So when you see this comet, when you see photographs of this comet, this is actually the resting site of the final resting site of the Rosetta spacecraft and its lander as it comes by the sun again. There's actually another comet fairly bright, although possibly not a good, certainly not a good naked eye comet in the sky in 2021. But as we continue through the solar system here, so this is Comet Leonard. Comet Leonard was discovered early in the year, and this is a picture of it. It's getting brighter now. I think it's near its perihelion. It's certainly near its perigee, its closest approach to Earth. In December, it's in the foreground, but fortuitously along the line of sight to these two interesting galaxies. This is one that's popularly called the Whale Galaxy, because I guess it looks a bit like a whale, especially in this picture. And this is the hockey stick galaxy, two interacting galaxies with the comet along the line of sight. Right, the comet is actually a few light minutes away in this image. The galaxies are like 25 million light years away, so they're quite in the distant background. Comet Leonard has no spacecraft associated with it, and will not. This is Comet Leonard, unlike Churyumov-Gerasimenko, is not a periodic comet. It's on a hyperbolic orbit. It's a one-time. I think its perihelion, its closest approach to the sun, will be in January, and then it's out of here. And if you think about it for a minute, it's hard to plan and execute and launch a mission to a comet unless it's periodic and you can actually plan over a period of years and match orbits with the comet over a period of years. The comets that just come in, swing around the sun, and go out are hard to catch. It's going to be hard to catch for a spacecraft. Well, we'll get out of the solar system here eventually. This is well, it says 50 light years, 51 Pegasi, and there is 51 Peg circled for you in the top center here. It's a picture of the Observatoire de Haute-Provence in France, where Michel Mayer and Didier Kerlotz worked and discovered the first exoplanet around a sun-like star. Around the sun-like star 51 Peg. So their discovery would have been in 1995. Actually, that's a good year. That's about the year Bob Nemiroff and I started up with APOD. Not that that was anywhere near as profound as the discovery of the planet around 51 Pegasi. 51 Peg B was initially the planet's name. It's, of course, at this point, there are 4,000 plus known exoplanets. Many of them discovered by space missions, like, many of them discovered by the Kepler mission. This one, obviously, based on ground-based, discovered by ground-based astronomers. 51 Peg was detected by measuring the Doppler shift, the wobble that the planet produces on the star's spectrum as the planet orbits. And so it was I think you can time it, you can determine its orbit, you can estimate its mass, the mass of a planet, and 51 Peg B was estimated to have the mass about, I don't know, about half, at least half, maybe more than half the mass of Jupiter. It orbits 51 Peg every 4-point-something days. So it's a sort of a Jupiter-sized planet that orbits its parent star closer than Mercury orbits the sun, much closer than Mercury orbits the sun. And it turns out to be sort of the prototypical, archetypical example of a hot Jupiter, which now that we've seen about 4,000 exoplanets, hot Jupiters are relatively common, not unusual, not exceptional for planets in planetary systems. Incidentally, I think Messier and Kalos got I think that was the 2019. They shared the 2019 Nobel Prize in Physics for this work with James Peebles. A little farther away, if you're going to venture a little farther away than 51 Peg B, I'd say you could get to M13 Globular Cluster. It's probably 20,000, 30,000 light years out in the halo of our own galaxy. And this is one of the brightest globular star clusters in the constellation Hercules, known as the Great Globular Cluster in Hercules. It's a very nice image of this really dense sphere of stars here. Now, these stars that you see with spikes around it are definitely in the foreground. This is a ball of a few 100,000 stars, let's say, in a diameter of about 150 light years. At the core, yeah, well, you can see the individual stars resolved in the image around the outside of the cluster here. But at the core, the density of stars is rather large. In fact, I think if you took a cube 3 light years on a side and put it at the core of a globular cluster like M13, you could probably count 100 stars within that cube. If you took a cube 3 light years on a side and put the sun at the center of it in the solar neighborhood, you wouldn't find any other stars. The closest star system to the sun, Alpha Centauri, is 4-something light years away. So it's very dense in the core of that globular cluster. Many years ago, a naturalist photographer, wildlife photographer, Roger Hopkins, sent this image to Astronomy Picture of the Day. It's an image he took at a wildlife preserve in upstate New York. I wish I could name it. Maybe Dave would recognize it. Of what he described it as what he thought sunset would look like if he lived on a world in the center of that orbited a star in the center of a globular cluster. Then I thought it was pretty clever. As you can see, as the sun is setting and the stars are beginning to come out, the sky is very densely populated with stars. I think what Hopkins has done here is he's photographed a flock of birds flying above the water here, and manipulated the photo to turn the black dots of the birds into stars, a flock of stars. Sunset in the middle of a globular cluster. Hanging around in the plane of our galaxy, you could travel to star forming regions like M16, the Evil Nebula here in one of Adam Bloch's nice images. This is a cluster of stars inside its sort of natal molecular cloud that the star cluster formed from. And you can see the stars as the stars, winds and radiation from the stars sort of sculpt away and carve away at the dusty regions. They compress the gas and all these dense features. Stars are forming inside these features. New stars are being born here. There's a famous Hubble image called the eagle's eggs of this particular formation right here, and another famous Hubble image of this extension here for star formation. In this the image here by Robert Eder, Eder has taken out all the stars that he can see. He's digitally processed them away to leave just the star stuff, the star forming material. In a nebula IC 443, it has this famous feature in it called the Elephant's Trunk Nebula. And although Eder has taken out all the stars he can see, there's still stars forming down inside the elephant's trunk here, which I guess you could see if you could look in infrared light. You would see some indication of the star formation going on inside there. These features as well. I only recently learned that the popular name for this is the elephant's trunk in IC 443. This is the caravan. These sort of star forming pillars are popularly known as the caravan. So elephant's trunk and caravan. If you wonder, well, let's look at it this way. If you were just in interstellar space near the sun, you could probably count one atom of hydrogen in a cubic centimeter. If you were to fly in your starship through one of these regions we see as these nice nebulae, maybe you would count in a cubic centimeter, maybe you would count 10,000 atoms of hydrogen. So they are quite a bit denser than the local stellar neighborhood. That's why we see them in, we still see the star stuff, we still see the nebulae. Of course, if you were to try to count the air molecules in the room you're sitting in a cubic centimeter of the room you're sitting in, you would count 10 to the 19th or something like that. So you would count 10 billion compared to 10,000 compared to 1 in our neighborhood. You were wondering how dense that was, if it would affect your travel plans at all. You have any travel plans to go here? I don't know. I'm a big fan of Star Trek, for example. And if my starship were going anywhere near here, I would put the shields up, as it were, because this is the Crab Nebula Pulsar, and it's been imaged in by the Hubble Space Telescope and by CX Chandra X-ray Observatory. So this is a mix of optical and X-ray imaging of the Crab Nebula Pulsar. It's and I would say this distance through this inner ring here is about a light year. So this is a pretty enormous, still a pretty enormous, basically a particle beam weapon almost. The pulsar is spinning 30 times a second. Its magnetic field is dragging this, is formed this torus of energetic particles. Relativistic particles are shooting out the beams perpendicular to the rotation axis, or along the rotation axis of the torus. Of course, the Crab pulsar is, and the Crab nebula is a supernova remnant. The Crab pulsar is the core of the collapsed core of a star that exploded around 10,000 years ago and was observed in records. There are records of it when its light reached Earth, and of course the nebula is the sort of expanding debris cloud. Shields up for a tour of the Crab Nebula Pulsar dome. Yeah, one of the problems with sort of using astronomical images to tour around the universe is, well, is sort of the vantage point is not, you're not really in control here, but I like this pair because, well, consider this, an external galaxy, the Whirlpool galaxy M51, very bright galaxy, once one of the original spiral nebulae that people would make drawings of. You can see the spiral structure in a large telescope and see it visually. You don't need to photograph it. It's one of the original spiral nebulae back when there was a debate as to whether these were actually external galaxies or just spiral-shaped nebulae within our own galaxy. They are, of course, external galaxies, 50 million light years away for M51. It has this nice spiral structure. You see all these red star-forming regions like the Eagle Nebula all along the spiral arms. And you see this spiral arm and dust go in front of a companion galaxy interacting with M51. You can tell that the companion galaxy, I think, is behind M51. It's not exactly in the plane of M51 because it looks like that dust structure goes in front of it. But if we had a starship, we could try to fly around and look at it from the side. And I think if we looked at it from the side, we'd see that this system really, from the side, looks something like this. This is a flat, this is the plane of a spiral galaxy. It's spiral arms. You can almost guess that these are spiral arms inside here. And this is a companion galaxy that it's interacting with along the side. So I think this is the side view. This is the face-on view for systems like this anyway. We can't really fly around them in the Starship, but we can figure out what they look like from a different perspective. I have actually forgotten, and don't see in my notes. Oh, is this 1543? The galaxy in the river, this is an NGC, has an NGC number. It's a bright galaxy, but it's in the southern hemisphere, not in Messier's catalog. It's in the river, it's in the constellation of the river. It's in Eridanus, if you were a fan of the southern sky. I may flip through here pretty fast. We're obviously visiting, we're obviously in extragalactic space here. This is a famous image of Messier 101 from the Hubble Space Telescope. It's a very high resolution image of the galaxy at its full resolution from a 2.4 meter telescope in low Earth orbit. And this is a pretty high resolution image of Messier 31. The galaxy's a little closer. It's about 10 times closer than M101. But this image, well, M101 was imaged by Hubble from low Earth orbit. This was imaged by Robert Gendler from his driveway in Connecticut with his 12-inch Cassegrain telescope. I don't know. I enjoy the comparison between the amateur work and the professionals. We've moved out a bit now. I think we're closing in on as far as we can go here. Galaxy cluster Abell 370, 4 billion light years away. Galaxies come in clusters, by the way. Where's a good place to find a galaxy? If you look out into the universe, the answer is right next to another galaxy. They come in clusters. They come in these large groupings of galaxies, which you see all together if you can look out far enough. The cool thing about this image is you're actually seeing beyond this galaxy cluster. You're seeing galaxies far beyond this foreground galaxy cluster, which is 4 billion light years away. The galaxies behind it are showing up as these streaks, these curved streaks. The gravitational mass of the galaxy cluster, Abell 370, is dominated by dark matter. And it's so massive that it's actually lensing. It's called gravitational lensing, predicted by Einstein's general relativity about 100 years ago or so. Anyway, we're looking, because of gravitational lensing, the cluster Abell 370 is acting a bit like a telescope lens, showing us light from galaxies far behind it, although stretched out into these long arcs. Spectroscopically, you can determine properties of those distant galaxies. So it's so thank you Einstein and gravitational lensing. Okay, I think I probably will come to the end of the tour here. I had to work this in somehow. This is a slide this is an image submitted to APOD not too long ago that was one of my favorites. I guess this might fit into a terrestrial, a more terrestrial travel talk. Basically, the pixels are the moon, as you might have guessed. The moons, it's all natural colors of the moon. They're just pictures of the moon taken at different altitudes, different seasons, different phases, arranged into, like I said, pixels in an image. You might recognize the image as the Mona Lisa, right? Which you would normally have to travel to the Louvre to see. But here you go, the Mona Lisa. And the way to see, I think the way to see it most easily, you could stand back from your monitor a bit, or you could just look until at smaller and smaller images until you might actually recognize the Mona Lisa. The tie-in with Da Vinci that really impressed me was Marcella has used for the darker pixels here. The moon, that's the color of Earthshine, for example. This is the bright crescent moon, and this is Earthshine. When you can see the moon by light reflected from planet Earth, you can see the night side of the moon. Da Vinci actually explained what Earthshine was 500 years ago. So the Mona Lisa in Earthshine from Leonardo da Vinci. And the end, it says the end. Let's stop here. stop here. This is it's actually an old image of the Chelyabinsk meteor flash. My goodness, that was in the Chelyabinsk meteor had an airburst over Chelyabinsk, Russia in 2013. Photographer out for a morning stroll happened to catch the airburst. I just like to end with that slide, Brian.
Well, that's a good place. You know, I don't remember which one it was. It might have been the DART mission, but a couple of months ago we had a webinar on. It probably was the DART mission about all these asteroids and the mission to go out and redirect, see if they can alter the course of
Yeah.
So we saw some of these videos during that one. That was pretty spectacular. So, well, we do have a number of questions here, and so let's get to some of them. And so we've got one question says, what makes some comets periodic and some just a one-time only?
I think comets. Questions. I think comets. There's a reservoir of comets in the Oort cloud, right? That's 100,000 AU or so from the sun. It's a big spherical cloud. We know you can plot their orbits. You can see where they came from. And the non-periodic comets come in from the Oort cloud. What put them out at the Oort cloud? I'm guessing that they're scattered out there from maybe from closer in the solar nebula when the solar nebula was formed. The periodic comets seem to hang out, or perhaps they were captured in interactions, or seem to hang out in the inside the orbit of Neptune, or near the orbit of Neptune, or even closer. And there are 100 or so periodic comets known. I don't know I should just say, Jerry, I don't know the answer to that question, but I know who to ask. You ask a planetary dynamicist.
There we go. So we had some interest in the nebula. I thought it was really interesting when you related the density of them, and speaking of Star Trek and some other science fiction movies, it seems like a common theme is that the spacecraft go and hide in the nebulas, and that doesn't really.
Hide in the nebulas. Actually, I did have one question in a talk years ago. Someone wanted to know. I was doing the travelogue routine, and someone wanted to know if they flew through one of these nebulae, would they need windshield wipers? Right? And that's what got me thinking. That's why you can answer a question like that, because that's what got me thinking. I don't know if you would need windshield wipers or not, but I do know that it's 10,000 atoms of hydrogen as compared to 10 billion molecules of air. So
yeah.
So there you
go. Still a pretty good vacuum.
Yeah. Still an excellent vacuum by 15 orders of magnitude.
Yeah. So kind of staying with that, and so we have a question about the hydrogen that were in these molecular clouds, and wondering, well, is that the same stuff that was in a nuclear bomb? If you were to travel through it, would the friction of the spacecraft possibly ignite it? Kind of in the same vein as the other one.
No. Only if you were traveling through it at some significant fraction of the speed of light and happened to run into one of those atoms of hydrogen, then I think you could get some sort of nuclear detonation. Otherwise, at normal automotive speeds, I don't think there would be any friction or any problem there whatsoever. Have I gone too far with that?
No, it's a good question though. It's it's
Yeah,
kind
it
of
is.
interesting.
Once
You know,
again,
and it could actually pose the question, well, are we talking about, ignition in terms of, then you'd need some oxygen to have
well, when you
then,
say nuclear bomb, I'm thinking about a fusion
Yeah.
bomb, a fusion reaction, a fusing two nuclei
yeah.
of hydrogen.
But it's a good question to think about the different processes that take place to make.
Yes, but you won't get that from friction like we
No.
think of friction. You won't get the fusion reaction from friction. You might at half the speed of light smack into a hydrogen atom and cause a lot of trouble there.
So kind of staying with the density of the nebula, and so we have another question: how is the density of a nebula determined? How do we figure that out from here?
Yeah, spectroscopy, the great tool of the discovered of astronomy, discovered in the 20th century. The motivating building all these large ground-based telescopes. Spectroscopes allow you to measure the intensity of spectral lines and identify the atomic species that they come from. So density, you get density and temperature out of modeling the plasma that produces the spectrum that you observe.
All right.
So that's how in the first place, the lines that you see are the lines that you see in the nebulae, for example, won't occur in the laboratory, except they're forbidden lines often, or combination lines. They require very low densities for the transitions to take place in the first place. So the fact that you see them at all, it means the density is very low. And then the relative intensities of the lines can let you determine exactly what the density is.
So we've got time for a couple more questions, and some of these I'm going to lump together, but here's the last kind of science question, and we'll kind of do some more practical ones. And so do dark matter and dark energy interact? And so you had alluded to that.
Oh, I see this. Yeah, dark matter and dark energy. Yeah, I mean, dark matter is called dark matter because we don't see it. We know it's there because it's gravitational matter. It influences the orbits of things. It's keeping all those galaxies in that cluster, in a cluster. It's doing the lensing, the gravitational lensing. Dark energy is the sort of additional energy that's producing the universe's expansion. That's sort of countering the gravitation on large scales and expanding the universe. So in that, dark matter is gravitational, and dark energy is causing the universe to expand, not contract. Yeah, they do interact.
Okay, next to the last question. And so a number of people have asked about how to go about submitting photos to Astronomy Picture of the Day, and what are the criteria for selecting them?
Submitting the photos, if you go to the website and you look at the navigation bar along the bottom of one of the picture pages, you'll see submit. And if you click that submit, you'll go to a page where it says mail to links. And the bottom line is just going to be submitting a photo. You should submit it by email to Robert Nemiroff and Jerry Bonnell. You should submit it to both editors so we both see it. If you want to give us both a chance. And the email addresses are in that submit link.
I just posted the link to the chat too.
Oh, thank you.
Thanks,
Yes,
Dave.
that's it. Submit 2015.
Awesome.
So once
Couple
they submit
versions.
them, what kind of criteria do you use to, because
Good.
I'm guessing that you get a lot of submissions.
Yeah, we do. Yes, we do. It's gone from right. I'd say in the early days, we definitely were not driven by submissions of images to Astronomy Picture of the Day, but now we are. It's the vast majority of images are submitted, and it's difficult to choose, and so we look for good technical images, but also we look for good topical images as well. And by topical, I mean there are conjunctions, eclipses, comets, things like that. So and so I do appreciate that. Well, there's only 365 days usually in a year, right? And so I would say we are oversubscribed by a factor of 10 or 20. There's 10 or each day. There's probably easily 10 images I would have put out for that day. So I have to figure out some way to choose. And like I say, it's tough, but it's not always. I mean, I don't really do it as a popularity contest.
Yeah. Well, you want to, pique people's curiosity, and
I do. And so what sort of images catch my eye? I don't know. I've always been a sucker for a big, beautiful spiral galaxy. How about that?
well, this might leads into the last question, and I apologize to the people whose questions we're not going to be able to get to. And so this question is kind of akin to asking which of your children you like the best. What's your favorite photo that you've published, and do you have a favorite? I guess it sounds maybe it's a spiral galaxy. So.
Could be. I could show it to you.
Oh, please.
I have it in my talk.
Oh, good.
Here, but all I have, so I'll tell you what I'm trying to do. And so if I mess up, you could jump in. I'm going to share my screen and I'm going to show one last slide from that talk.
All right.
Okay.
Excellent.
And when I do that, oh, well, that was easy. Let's go on to a few backup slides. I'd say I don't know. I have trouble asking what's your absolute favorite image, but let's pick this one. This would come close. This would come close, and I can tell you why I like this one, and maybe it will it'll help the selection question. First off. It is a spiral galaxy, although this one is a spiral galaxy on edge, right? NGC 5907. So this is the plane of the galaxy. And if you could see it face on, not edge on, you would see that it had spiral arms. Spiral galaxies have this very thin plane. This is the ghost of a galaxy. This is the ghost of at least one galaxy that was orbiting this spiral galaxy and orbited a few times before it was consumed by the galaxy. So this sort of galactic cannibalism is, I think, our understanding today is basically how large galaxies form by eating small ones. And in this image shows the star streams, the sort of fossil star streams from the galaxy that looped a few times through there before it was absorbed into the spiral galaxy. What I think is, and so the picture is interesting scientifically. I think it's very aesthetic. I think it's a pretty picture. Okay, it's well done. It's technically good. It's aesthetic. This picture represents a discovery, a major discovery by an amateur professional collaboration of star streams around nearby bright galaxies. This is something that couldn't be discovered by large professional telescopes because they're not fast, wide field sort of instruments. So I like this picture. This is the perfect astronomy picture of the day. Climbs the mountain from two sides. It climbs it from the science side and the aesthetic side and reaches that peak. And this is that peak for me. Can you still hear me?
Yes, we can.
My screen just went blank.
Yeah, it says that it went in. So I guess that's a cue that you should stop sharing.
I did mention that I was supposed to be the bedtime protector for Jerry, so I should say.
Oh, it's my bedtime. Thank you, Dave.
Yes, we are past time, which but thank you very much. And so that's all for tonight, everyone. Thank you, Jerry, for joining us this evening. And thank you, everyone, for tuning in. And so our next webinar is, we're going to have to wait just a little bit, is Monday, January 10th, when Jessica Taylor from NASA's GLOBE program and Langley Research Center will share with us how you can contribute to NASA's science when clouds take over the sky. So, and you can find archives of each of these webinars in the Night Sky Network website in the Outreach Resources section. Each webinar also features additional resources and activities. You can also find all of these webinars archived on the Night Sky Network YouTube channel. So keep looking up and we will see all of you next month. And so thank you very much for joining us. And thank you, Jerry, for joining us. Great.
You're welcome. Thanks for inviting me. Thanks, Brian. Thanks, Dave.
Yeah,
This is a great time. Thank you so much.
Sure.
Of course, been a big fan ever since the beginning of the internet, basically. Late 90s for me.
Late 90s.
I know technically earlier.
Last century.
And I should also mention that a few years ago, the Astronomical Society of the Pacific gives out awards. And so a few years ago, I don't remember what year, maybe it was 2015. It seems like a lot of things happened in 2015. But Jerry and Robert received the, what was it, Dave? The Klumpke-Roberts Award for
Klumpke-Roberts Award.
Yeah. And so that was, we